Welcome to my talk on cellular mobile architecture for beyond 5G, some learnings from IEEE P1930 and P2061 standards. The agenda of this talk will be that we will first discuss the growth in the mobile data traffic that has happened in the recent years. Also, the coexistence of multiple radio access technologies that are going to be there in the next generation heterogeneous networks, that is 3GPP radio access technologies like LTE, 5G NR, and non-3GPP radio access technologies like IEEE Wi-Fi. Then we will discuss what are the limitations of 3GPP 5G system architecture, some key features of IEEE P1930 and P2061, which we believe can be used to design a scalable network architecture for beyond 5G. If you look at the mobile data volume growth that has happened in the recent years, in fact, in 2015, it was forecasted that the mobile data volume will be about 51 hexabyte per month. And in fact, we have exceeded that. We have about 65 exabytes per month in year 2021. The same growth, we have seen it in the mobile subscriptions, PC, tablet subscriptions, and so on. So the actual data volume exceeds the forecast that was done in 2015. If you look at developing countries like India, even India has seen a continued growth in the mobile data consumption. In September 2021, the total number of mobile broadband subscribers was 770 million, and the mobile data volume in the year 2020 was 9.4 exabytes per month, which jumped to 12 exabytes per month in year 2021. There are primarily two driving factors for this growth in the mobile data. One, of course, increasing number of smartphone users, which has led to increased data usage in terms of both internet data and audio video data. And secondly, in the recent years, we have seen a growing footprint of cellular broadband network in rural areas too. And that has also led to a growth in mobile data consumption. What will be 5 years down the line? If you just try to make a rough estimate of mobile data consumption in year 2027, most households, we believe, that will have mobile broadband access by 2027. In India, because the fiber is not available in a ubiquitous fashion, we don't have fiber to each home. Cellular phone is the primary broadband access mechanism. And in that context, therefore, architecting a cellular mobile network for handling the large volume of data traffic that we expect in a country like India is the key. In 2027, India may have a population of about 140 billion, and assuming average 4 person per household, the total number of households in the country may be about 35 million. If we do a very conservative estimate, where we assume that the required data rate per household will be about 2 megabits per second, by this conservative estimate, the monthly data requirement of the entire country comes out to be 23 exabytes per month. In a more realistic estimate, where we assume that 5 Mbps per household will be needed, and this is also, in fact, I would say that it is on the conservative side only. the mobile data requirement of the country comes out to be 57 exabytes per month. So even a conservative estimate indicates a huge data volume in 2027. In fact, 275 exabytes annually. And as I mentioned, designing a scalable network architecture for such huge data volume is very, very critical. We will need large number of data plane functions for packet processing. Now, let us review whether the existing architecture are capable of handling this kind of mobile data volume. If you look at the existing 3GPP 5G architecture, it is basically a disaggregated RAN. The disaggregation has been done of GNB. GNB has been disaggregated into CU and DU through an F1 interface. Even the GNB CU has been broken up into GNB CU control plane and GNB CU user plane by following the principles of software-defined networking paradigms. And the GNB CU control plane and the GNB CU user plane are connected through even interfaces, and GNB CU control plane is connected to GNB DU data plane through F1C and F1U interface. So this is actually a disaggregated RAN architecture. The same disaggregation or a similar disaggregation is also there in the ORAN. In ORAN, we have a open front haul interface between ODU and ORU. So essentially, we have an architecture for disaggregated RAN across F1, E1, A1, E2 front haul interfaces. The question that arises is this architecture good enough to handle the projected data volume that we just talked about, let us say in a country like India? And secondly, very likely, we are likely to have heterogeneous network where we will have coexistence of multiple radio access technologies, at least Wi-Fi and LTE or 5G NR. So is this architecture good enough for handling this multi-RAT access network? Let us look at the existing 3GPP 5G architecture more closely. If you look at the existing 3GPP 5G architecture, the core does provide the unification of multiple RAT. It is a converged core, and it does provide a unification, multi-RAT unification. However, there is no unification at the RAN level. The core does not have an integrated and comprehensive view of the radio access networks. And this leads to fragmented decision making in the RAN. The second problem is that between radio and core network protocol stacks, there are these tight and proprietary coupling interfaces, as is shown in this figure. Moreover, there are these RAT-specific interworking functions. For example, there are these N3IWF for untrusted Wi-Fi access point, TNGF for trusted access point, WAGF for a wireline access. So as you can see that for each specific RAT, there is a specific interworking function. Finally, there is also a loss of flexibility. For example, it is not possible to connect a 5G RAN to the 4G core directly, or if you want to connect it directly to the internet without core, that is also not possible in the existing 3GPP 5G architecture paradigm. Let us look at, how the 3GPP 5G architecture handles the dual connectivity and load balancing. In dual connectivity, where the UE is connected to two radio interfaces simultaneously, in 3GPP, there are multiple variants are there, and these variants are RAD specific. For example, there is LTE variant, there is a LTE WLAN aggregations, there is MRDC, and there are differences across all these variants. Moreover, since the core does not have a unified view of the RAN, to achieve this dual connectivity, extensive coordination is required between ENB, GNBs, and Wi-Fi access point. And this leads to complexity in implementation. Similarly, if you want to achieve the load balancing across these different radio access technologies, then that scheme is also distributed across the E node B and the GNBs. And the load information will be typically exchanged over X2 or XN interface. No load information can be exchanged in the absence of these interfaces, and the core does not have a view of the load which is present on different radio access technologies, since it doesn't have a RAN level information at the core. Moreover, there is no mechanism for load balancing across the 3GPP and non-3GPP radio access technology. That means, you can't achieve a load balancing between Wi-Fi and LTE or between Wi-Fi and 5G NR. No such mechanism is available in the existing 3GPP 5G architecture. Essentially, the existing architecture, dual connectivity and load balancing are distributed scheme. These are RAD specific variants, and obviously, therefore, there are limitations. No load balancing is possible across 3GPP and non-3GPP radio access technologies. And there is no network entity which has a unified view of the RAN resources. This leads to, as I already mentioned, fragmented RAN control, then LTE E-node Bs or 5G NR GNBs or Wi-Fi access point, they take decisions independently. And this leads to suboptimal resource utilization and implementation complexity. Now, if you want to design an architecture which is scalable and beyond 5G cellular mobile systems, then there are a few points that we would like to elaborate. First of all, in a multi-RAD radio access network, how we can disaggregate a multi-RAD RAN? Should we have a unified multi-access RAN? That means, is it possible to achieve a unified treatment of dual connectivity, load balancing, etc.? Should we decouple the RAN from the core? That means, should we allow, let us say, a 5G NR RAN to connect directly to the 5G core for non-standalone deployment? Now, why do we need a core? We need a core because mobility is anchored at a core and authentications and access control are done from the core. But as I mentioned, that where in a country like India, where cellular broadband is the primary broadband access device, a large percentage of users are using the broadband when they are stationary, when they are sitting at home, and they may not be mobile. In fact, in a rural setting, the mobility itself is limited to very, very low mobility. So a large percentage of mobile users may not be mobile, in fact. Okay. And then the question is that, can we have the flexibility where we can bypass the core for such fixed users and achieve a very simple connection to the internet? Are these possibilities, can be taken care of? Now, in order to address these questions, I would first like to review the IEEE P1930 standard, which is a standard in making. So if you look at the RAN disaggregation and unification, the RAN of most radio access technologies, they perform similar functions in 5G. And these functions could be security, optimization functions, interworking with the core. And the question that we ask is that, can we disaggregate the RAN along these simpler functions? And by doing so, does it help in load management? Does it help in dual connectivity? Does it help in unified treatment of different radio access technologies? Now, here is a simplified representation of P1930 architecture. In a P1930 architecture, we have a RAN disaggregated data plane. There is an SDN middleware, and there is a unified multi-rad RAN control plane. The data functions are basically organized in a modular fashion. There is a medium access control functions. Of course, this includes the MAC layer, physical layer, etc. For example, this is 802.11 MAC could be there. Here, LTE base station functions can be there. And here 5G NR base stations functions can be there. And then these are adaptation functions. This is essentially a RAN adaptation function which does the job of link control, ARQ, security functions, which does the job of encryption and integrity protection, and optimization functions, which does the functions such as IP header compression, etc. And finally, interworking functions for interworking with the core. There is a controller there, and this controller is responsible for controlling and managing a subset of these modular functions. So in P1930, the disaggregation has been done along these simpler functions, that is adaptation functions, security functions, optimization functions, and interworking functions. How does it help? Let us say that a UE is connected to two base stations. For example, as is shown in this figure, it is connected to 802.11 Wi-Fi and LTE or 5G NR base stations. Now, when you want to route the traffic from the core, then it can be routed from the same interworking, optimization, and security functions. We need not have, different security functions or different optimization functions or different interworking functions for this. Only when it leaves the security functions, it can be delivered through two different base stations via these two adaptation functions. One adaptation for 802.11, another adaptation for LTE. The control plane can actually set up the data path through these access network elements. And as we can see here, that the dual connectivity of this UE through Wi-Fi or LTE gets simplified in a very, very significant way compared to the dual connectivity where, in an existing 3GPP architecture. The P1930 also achieves a multi-rad unification and virtualization. There is an SDN middleware. This SDN middleware is between the control and the data plane. And this is to virtualize and unify the multi-rad RAN data plane. Essentially, it provides an abstract model of the data plane through these virtual entities. For example, here the Wi-Fi base station has been virtualized, LTE base station has been virtualized, 5G NR base station has been virtualized, adaptation function virtualization is here, security function virtualization is there, optimization function virtualization is there, and interworking function virtualization is there. It virtualizes underlying data plane resources, and it unifies the control and management of the multi-rad RAN by achieving these virtualization. Essentially, P1930 provides a unified view of multi-rad RAN. It has an SDN middleware, which I already mentioned, provides an abstract model of underlying RAN through virtual entities. It has a multi-rad SDN controller, which does control and management of the access networks. It has a management and orchestration function, which is used to orchestrate and manage the middleware over the RAN infrastructure, and finally the radio access network infrastructure, which comprises of access point, base stations, interworking functions. Moreover, we can actually do network slicing, and these virtual entities, they can be actually distributed across different logical networks by creating these slices, and these slices are orchestrated by orchestration function in P1930. Each slice, in fact, is controlled by a different SDN controller. And you can have slices depending upon the QoS attributes also. For example, blue slice can have a different quality of service parameters, and an orange slice can have a different quality of service parameters, and so on. In summary, P1930 actually enables a very scalable access networks through modular reusable data plane functions. It has a disaggregated RAN, which has been disaggregated along reusable data plane functions. It enables virtualization of data plane through SDN middleware, and it provides unification of various RATs at the RAN level. And by doing this, we have a significant performance improvement in terms of better load distribution, because now this multi-RAT controller, multi-RAT SDN controller, has a unified view of the RAN, and therefore it can do the better load distribution across granular functions. Performance is improved. Similarly, in terms of dual connectivity, we have a very simplified and a very easy to implement architecture. Now, let us look at some of the key features of P2061, that is Frugal 5G network. The original intent of the IEEE P2061 standard was to address some of the requirements of the rural access. That is, the network should be cost effective, it should be affordable. Then we don't need high speed mobility, only low speed mobility, so limited need for mobility. In a rural setting, we need a large coverage area support. Also in a rural setting, there may be clusters of settlements, so the population is actually sparsely populated. And with clusters of settlement, we need energy efficient solutions. We need support for localized communications and local content generations, and ease of manageability. So this is an instance of IEEE 2061 Frugal 5G architecture, where there are these small cells, and these small cells could be Wi-Fi cells, which are located in these clustered settlements. These Wi-Fi cells provide high-speed connectivity, and these small cells can be wirelessly backhauled using a middle mile network to a fiber point of presence, and where there may be a macro base stations. The macro base stations can provide an umbrella coverage. Now, we can have a control and management at the edge also, and this edge control can actually enable, the local communication support and the local management and control. So the core network essentially can have an NFV based cloud, and as far as the access and the edge network is concerned, it comprises of macro base station and Wi-Fi access point at access, a middle mile network, and a NFV based edge network. So this has a very flexible implementation. It enables both macro cell and Wi-Fi access, and a wireless middle mile to carry the Wi-Fi access traffic from these clustered settlements of villages to the fiber point of presence. Intelligence at the edge will enable the local communication support, and also the direct internet connectivity from the RAN. We can actually bypass the core. And SDN based unified control provides RAT agnostic unified interface towards core. It also decouples the core from the RAN, and it provides a unified multi-access control at the edge. So these are some of the key attributes of the Frugal 5G network, which is getting standardized in IEEE P2061. Now, in the context of 3GPP, how we can realize a Frugal 5G network? Essentially, we replace the proprietary interfaces. So the proprietary interfaces which are there in 3GPP between the radio and the core network protocol stacks, those proprietary interface can be replaced by these open flow switches. So this is how we have proposed that. For example, this is a GNB NR radio interface. This is a Wi-Fi radio interface, and there are other radio interfaces. As you recall that in 3GPP, for each radio access technology, there was an interworking functions. That is, for example, for the Wi-Fi, there was this N3 IWF interface. Now, by introduction of open flow switch, it can replace the proprietary interface and enable a unified interworking function. Similarly, by introducing open flow switches at the UE, it can replace the proprietary interface. And then we introduce an SDN based RAT agnostic controller. So this is a RAT agnostic controller at the core, which can enable a unified RAN level control and management. So since this controller has a unified view of the RAN, it can actually enable the control and management in a much more flexible fashion. Finally, because we have replaced the proprietary interface with the open flow switches, these open flow switches actually enables the decoupling of UE's communication with the core network from its communication with the RAN network. And because of this, it is possible to connect the UE directly to the internet without going through the core network. If you look at the existing cellular technology, that is LTE or 5G NR, they necessarily require the support of the core networks. They cannot work in a standalone manner without the core networks. But on the other hand, the 5G flow architecture allows the usage of cellular technology, for example, 5G NR, without actually involving the core networks. The 5G flow controller, this flow controller here, it sets up the flow entry and creates the radio bearer to enable the direct connectivity at the internet. So in summary, open flow, a modified version of this, can be used to decouple the RAN from the core. Though it is not necessary to use open flow, even other protocols and mechanisms can also be used. But basic idea is to replace the proprietary interfaces between radio and core network protocol stack through interfaces such as open flow. The remaining existing 3GPP protocol can continue to be used without any change. In fact, this open flow augments the existing architecture without modifying them. It enables a flexible mobile network architecture. In fact, any RAN can be used with any core. And we can use the core selectively. We can use the core only, for the purposes of mobility and for authentication. There are other use cases of this 5G flow. For example, as I just mentioned, it enables the direct connectivity to the internet. Okay. It enables a simpler non-standalone implementation. And for example, it can also be used in the captive networks without, the deployment of a complex core. So what are the key design principles in P1930 and P2061? They have a disaggregated multi-rat RAN. Essentially in P1930, we have disaggregated the RAN across modular and reusable network functions and thereby enabling a scalable architecture. SDN paradigm is being used where RAN resources are virtualized through an SDN middleware. There is a unified multi-rat RAN control, and the proprietary interfaces between the radio and core networks are replaced by open flow switches. And finally, there is a decoupled RAN and core. This enables a very flexible architecture. In fact, it enables interworking of any RAN with any core. And it also enables the direct connectivity from RAN to the internet for stationary and low mobile or nomadic users, bypassing the core. And finally, RAT agnostic common interworking function are presented towards the core. So these features which are present in P1930 and P2061, they enable a very scalable architecture which can be designed to handle the large volume of the data traffic that we expect in the coming years in a cellular mobile network. I believe that disaggregation of radio access networks across simpler function and having a unified view of RAN at the core network level, at the controller level, so that we don't have the fragmented decision making, and virtualization of RAN resources and enabling network slicings, all these features actually are the way to design the future next generation cellular mobile architecture, which is likely to be a heterogeneous architecture with multiple radio access technologies, at least 2 radio access technologies definitely, that is Wi-Fi and LTE or 5G, if not 3G and so on. In such a multi-rat radio access network scenario, it is critical that we have a scalable, unified multi-rat RAN control. And as I mentioned, that some of the features which have been or which are getting standardized in P1930 and P2061 can perhaps be looked to design a next generation scalable architecture for beyond 5G. Thank you.